All right, so yeah, let's get started. Let's review what we covered in the last lecture. So basically, in the last lecture, we'll continue talking about the property of the noise, right? And then we talk about the detection in. We start talking about the detection in the AWGN channel. Okay, and for the noise, so the third property that we care about is that so any linear processing of a Gaussian random process will be a Gaussian, right? So we have seen two examples. So the first example is that, so if we do a linear filtering on n of t, so which is our Gaussian noise, and then so the output will be another random process, right? And we can show that this random process is still a Gaussian random process. Okay, so. And so then it means that the input is a Gaussian random process. Then after some linear processing, then the output is also a random Gaussian random process. And another example is that, okay, so if we do this kind of operation, so we're going to see that this is exactly what we do for the receiver, right? If we multiply a deterministic function on our n of t, right, and then we do an integral, okay, and then clearly, the output is a number now. It's not a function of time, right? And this number, we can show that this is a Gaussian random variable. Okay, so that's what we said. Okay, so any linear operation on a Gaussian random process will give you a Gaussian, right? So this Gaussian basically means that it's either a random Gaussian process or a Gaussian random variable, right? Okay, great. And another important property of the Gaussian random variables is that so we have two concepts here. So one is independent, and then another one is uncorrelated. We can see the independent basically means this, right? So for the PDF, actually the joint PDF equals to the multiplication of each individual marginal PDF, okay? So actually you can consider that as a definition, but actually that is not a definition. It's a result of the independent, but it doesn't matter for our class. So let's assume that's a definition, okay? And uncorrelated basically means that the expectation of two random variable x times y, so that equals to the individual expectation multiplies together, okay? And clearly, so this is a weaker condition compared to the independence because the independence can imply that, right? Okay, great. And in the case of the Gaussian random variable, because the Gaussian random variable is determined by its mean and the covariance, so basically the second order, right? So we can show that the uncorrelated and the independence, they're equivalent, right? So in Gaussian, for the Gaussian random variables, so if you can show they're uncorrelated, it basically means they are independent, right? So it's a both direction, okay? So that's very nice. And in our class, for our random Gaussian random noise, so basically we're going to treat it as a zero mean wide Gaussian random process. Right, so basically, so we're gonna assume the mean is always a zero, right? So in practice, if the noise of the mean is not zero, we just pass through a filter to filter out the DC component, right? Then we're good, okay? And from the wide property, so basically it means the follows, right? If it's wide, so we compute it, right? So basically. So the autocorrelation function of nt would be equal to 0 if tau is not 0, okay? And clearly, because the mean of n of t is 0, then this guy equals to that, okay? And from here to here is the definition of the uncorrelated, right? Therefore, we can derive that. So if if nt is white, then it's uncorrelated, okay? And if they're uncorrelated, as we said, they're Gaussian as well, right? So it basically means that nt and nt minus tau, they are statistically independent if tau is not 0, okay? So is that logic clear? So basically, in our case, so all the noise, they are independent in different time slots, okay? And now let's summarize. Let's summarize it a little bit. So basically, this is our transmitted message, right? And after transmitter, so we'll have this is our transmitted signal, okay? And then we'll add some white Gaussian noise onto it, right? And nt is a random process. Then we got r of t, right? And this is our received signal. Okay, and now our focus so given all of this model, right? So from now on, we'll assume NT is a wide Gaussian noise, right, which is a random process, right? And RT is our received signal. Okay, those are important. So now we're gonna focus on how can we design a receiver here, then to process the RT to determine which one is sent, okay, either 0 or 1, okay? And this is our agenda for now. Okay, and we start talking about this a little bit. So basically, what we do here is as follows. So we apply this kind of structure for our receiver, so as we discussed before, okay? So what we do is that we use a fixed function or deterministic function, multiply our received signal, and then we do an integral, okay? And after this operation, so we get R, right? So that's not a function of t anymore, right? Because after this operation, so we have a number here, okay? And you can see this operation is nothing but an inner product, okay? So if we do an inner product between R of t and f of t, then we get R, right? So which is a number here. So basically, R is a representation of R of t, right? And using f. So you can understand that in this way. So we're going to see it more and more clear later. So okay, and then after this, we're going to see. So we're going to design a decision rule based on the received R. Okay, let's say what value of R we should determine that as a 1, and what value of R we should determine that as a 0. Okay, so that's basically what we're going to do. Okay. And the next question is that, okay, so the integral part is easy to deal with, right? But what is f of t, right? How can we design this f of t, right? And what kind of f of t is optimal, right? And should we just have one f of t here or multiple f of t, right? Is one enough or not, okay? So basically, that is our goal here. And basically, so if we do some simplification, so we can get this, right? So basically, R of t clearly equals to Si of t times plus N of t, right? And if we break it, because it's an inner product, then we're going to have this plus that, right? And N of t is noise, that we know, okay? And so we denote this guy as a noise, right? This is a scalar, right? It's just a number. And this is another scalar, we denote that as Si, okay? So the inner product between Si and F, so is Si, right? Which is not a function of t. Okay, and given this two, so we can compute the noise, capital N, right? So we compute that in the class. Our class, because we know N of t is a Gaussian random process, right? Then after this linear operation, so we know capital N of N is distributed as a Gaussian, right? It's a Gaussian random variable, right? Then to characterize what exact the distribution of N is, we just need to compute the mean and the variance, right? So the mean is 0, so we computed in our last class. And the variance, there should be square here, I've missed. So the variance here is N0 over 2 if we assume the norm of our f of t is 1, okay? And in our case, so this is always 1, right? So we're going to design it as this is 1. Okay, great. And now we can see the distribution of N is a Gaussian distribution with mean 0 and the variance N0 over 2. So do you still remember what is N0 over 2? Yeah, it's a spectrum, power spectrum density, right? Remember, so yeah, let me remind you a little bit. So the power spectral density of our noise, so we assume that is N0 over 2, right? The autocorrelation function of our noise is N0 over 2 times delta tau, okay? So this is nothing but the power spectral density, okay? So if we, and after all the process, so we can see that the noise variance just equals to this number, okay? So this is identical as our power spectral density. All right, and we know that R equals to Si plus N, right? And Si is a constant, so the distribution of R is another Gaussian distribution with the mean of Si and variance of N0 over 2. Of course, given Si is sent, right? If So if I is 0, then here will be S0. If we have S1 there will be S1. Okay, so that's how it looks, right? Okay, and this is very important, right? So basically, up to now, we could compute the statistics of R. We know exactly the distribution of our received signal if we know which one is sent. Okay, so remember that. This is very important. So we're not there yet to determine, okay, so based on the value of it, so which I is sent yet, right? But we know the distribution of R given which signal is sent, okay? Great. Yeah, and we started talking about one example. It's a simple example of a bipolar NRZ code, right? So basically, we assume S0 is this, and S1 is this, right? For example, when S0 is sent, we can consider that we send a 0, okay? Or we send a 1, and vice versa for this one. Okay, and there's an important property of it. So because of this bipolar NRZ coding, so you can see, so we satisfy this property. So S0 equals to minus S1, right? So that's called antipodal. So this is kind of important, right? So any signal satisfying this property for binary, so we call that antipodal, right? So later on, we're going to introduce some property. It turns out that it doesn't matter, what kind of exact waveform that we're using there. As long as they're antipodal, there will be some nice property that we're going to see, right? Great. And in particular, so we determine ft as S0 over S0, the norm of S0, right? So consider that is given now, so far. Okay, so we're going to see why that makes sense later, maybe, right? But this is kind of an optimal design in this kind of system. Okay, and the optimality is in terms of the signal-to-noise ratio at the receiver. Okay, so we're not going to touch a lot on that, but actually this is a very good design. Okay, so now basically what we're going to do is that let's see whether this design makes sense or not. Right? So based on this design of FT, so whether we can determine which one is sent from the transmitter. Okay, so that's the idea. Right? Okay, very good. Okay, so today our agenda is to continue talking about the detection in the AWGN channel. Today is our lecture number 33. Detection in AWGN channel. Okay, so we're gonna continue. Okay, great. Maybe we can draw this to remind you. So this is S0 of t, and this is S1 of t. Okay, and ft equals to S0 of t divided by S norm. Right? You can do S1 here as well. It doesn't matter. Okay, great. Okay, so now let's see what ft exactly is, right? So in order to compute f of t, then we need to compute this norm. Okay, let's see what does this norm is. What is this norm? Let's see whether you remember how to compute a norm. Okay. Okay, great. so this basically equals to what? Right, the integral of the square of this guy, right? And here the integral is from 0 to t. And within 0 and t, and this guy equals to a and dt, a squared, right? And this is nothing but a square multiplied t, okay? So that's the norm square. So basically this will just give you what? Square root of it, right? So a times square root of t, okay? And so by the way, so do you remember what is this formula is? Or this? We do a square. The integral is from actually from negative infinity to plus infinity, right? What is that? Inner product. Very good. Inner product with itself, right? But what's the meaning of it? Yeah, maybe it's too far, right? Exactly. So that's the energy, right? So basically, so this is very, very important. So it's one of the most important metric in the communication system that you're going to see later. So we denote that as E, okay? So we need, so the benefit of doing this is that later on, we're going to characterize lots of stuff using the energy of the signal, okay? So you can see later, it doesn't matter what kind of shape here we use, right? So we're going to characterize everything in terms of the signal energy, okay? So this is the signal energy, and denoted by E. Then we can see this guy is nothing but square root of E, right? And given this, so let's see what ft equals to exactly. So basically, we have S0 here, and we normalize it by this guy, right? So we have A as the amplitude, and divided by A times square root of t, right? So basically, so ft look like this, right? So basically, we have the same shape here, but the magnitude here is 1 over square root of t now, right? So this is our ft, right? Right, that makes sense? Okay, so now let's, so this is our ft, right? If we want to write it, so f of t will just equals to 1 over square root of t, when t between 0 and capital T, and 0 otherwise. Okay, so now let's double check. So see whether our choice makes sense or not, right? Let's compute the norm of f of t. See, so remember that, we want this equal to 1, right? Then the noise, the variance of noise, or the variance of the received signal can be squared not over 2, right? So let's compute this guy. So basically, the square of it is 1 over t, right? And dt. So basically, this equals to t multiply 1 over t, then that equals to 1, right? So we're all good. So this is 1. Okay, great. So now, given f of t, so you can see, we treat f of t as kind of like a base for our signal, right? It basically means that we can represent our signal using f of t, right? Let's see whether we can do it or not, right? Let's see how we can represent our transmitted signal using f of t. So basically, so we can think ft is a basis for S1 of t and S0 of t, right? It basically means that we can represent our signal using f of t. So for S0 of t, so you can see the only difference between S0, this, and ft is that, so we have a difference in terms of the magnitude, right? So the magnitude is already this one. So in order to get a here, so we just need to multiply a times square root of t, right? So basically, S0 equals to a times square root of t, ft, right? And S1 of t equals to minus a times square root of t times ft, right? Then we can represent S0 and ft using our ft, which is called a basis. Okay, great. That clear? All right. So if that is clear, so now, so remember, our received signal R, so which is after the integral, equals to Si plus n, right? So now let's compute Si. Okay. So now we have two Si. So we have S0 and S1, right? Let's see what S0 equals to. So S0 is nothing but S0t, the inner product between S0t and Ft, right? Let's see, what does that equal to? Okay, so basically, again, so now basically what we do here is that we use this and multiply that, right? And they have the same width, and the only difference here is that we have a here, and we have 1 over square root of t here, right? We just multiply this together, right? Then we're going to have a times 1 over square root of t, right? And the integral is from 0 to t dt, right? And let's see what that equals to. So basically, this equals to a over square root of t, then multiply this, right? T, so that equals to a times square root of t, right? That is our S0. Okay. Now look at this number. So what that is? What is that? So basically, that is the same as this guy, right? Look, they are different, right? So this is a norm of S0 of t, but that is S0. There's no t there, right? Then basically, so they have the same number here, so we can write, so this equals to square root of e, right? So we can reuse e here. And similarly, so if we use S1 here to compute, we can compute what S1 is, right? So S1 equals to the inner product between S1 and Ft, right? Because S1 is just the negation of S0, right? So we can see this guy is nothing but the minus square root of e, right? So the value of S0 is square root of e, and the value of S1 is minus square root of e, right? That makes sense? Okay, and and given this, so we can write the distribution function, okay, of R, right? So we know R is a Gaussian distribution with mean Si and variance n naught over 2, given what is sent, okay? Yeah, I will remove this. Okay, let's say we assume S0 is sent. So normally we say it's transmitted. We use Tx to represent what is transmitted. Okay, so in this case, we know R, right? Remember, R equals to this, right? Si plus n, okay? And so R will be distributed as a Gaussian distribution with, if S0 is sent, so here should be S0 and n naught over 2, right? But S0 here equals to square root of e, right? And similarly, so if wrong. Given as 1 sent, okay, and then gamma will be distributed as another Gaussian distribution with minus square root of e, and then n naught over 2, right? So now we know exactly what the distribution of R here. So and if I want to look at this, so we can draw it, something like this. So say this is this is a distribution of the first one, right? So this guy is square root of E. Okay. Yeah, this is the PDF of R given as 0 is sent. Okay, and for this one, it's minus square root of E, right? So this could be something like this. Should be symmetric. Okay, and this guy is given as 1 of T. S1 is sent. Okay, yeah, this is the PDF of this too. All right, any questions so far? Okay, if no question, let's see. I'll just briefly mention another example. So far, we just seen like the bipolar RZ case, right? So actually, we have some other waveform that we use more often than that. Maybe. So another example for this exactly, how to say, so we can get exactly the same distribution is the so-called binary phase shift keying. Or call that BPSK. So I haven't heard of that. Yeah, so for BPSK, so the idea is identical, but the difference here is that we use another waveform to represent S0 of t and S1 of t, right? For the first one, so basically what we do is as follows. So let's say we have the same definition of E, so which is the energy of the signal, right? So basically we assume S0 of t equals to this guy constant multiplied by cosine 2 pi FCT times PT here. Yeah, I'll explain what PT is. So, and then for S1, we have almost identical thing, 2 pi FCT, but it's called phase shift keying, right? So basically, it's a kind of it's a phase modulation, PM, right? So basically, we change the phase here, so we add pi, okay, times PT, and we assume the PT, this signal, is this one. Right, this is our PT. Right, we'll just pick, this length of this signal. Okay, so this is what we got. Okay, so now let's see for the S1 here, right? So we have a cosine something at a pi, right? So can we, remove this pi? Right, so cosine something plus pi equals to what? Sine? No, really. Yeah, cosine shift like multiple of pi over 4, the quarter of pi should be sine, right? So if it's shift, a cosine shift the opposite, right? Then yeah, what we got is negation of it. We have 2 pi FCT, so we can move this pi t, right? And you can see that, so here S0 equals to this, S1 equals to negative of this, right? So we're still antipodal, right? Then we have the exact same thing as what we discussed before, right? So you can see this one still antipodal. Okay. So then basically if we keep the computation, so we can see that, so given all of this coefficient, So we're going to see that S0 here without t equals to square root of e, and S1 equals to minus square root of e. And everything will be identical as that, right? So if we draw a distribution of R in that case, it will be exactly the same thing here, okay? So this will be true for any antipodal signal, okay, if we design in the right way. Okay, is that clear? Any questions? Okay, great. And now let's see something interesting. Okay, so now we know the distribution of R, right? You kind of know the statistics of R given what is sent, okay? So the next question is that, so given what we have known so far, how to optimally make a decision about what is sent. So you can see we're not quite there yet, right? Because we know the distribution of R given what is sent, but we don't know what is sent, right? It's kind of, contradictory, right? So, but this is what we know so far. So we're gonna see, okay, given what we have known so far, how can we design a decision rule to see which one is sent, okay? So our goal is to answer this question, okay? How to optimally make a decision about what was sent. Okay, so we need to make this decision from R, right? So that is R received signal. Okay, so now we need to clarify one thing. So we say optimally, right? So what does this optimal mean? Right? So the optimal here basically meaning that we're going to minimize the probability of error, right? Minimize the probability of error. Okay, so that's our goal. Right? And now let's see, so how can I do that? By the way, so the probability error here, yeah, maybe I'll use another color. So this basically means that, so what is the probability that SI hat, so that is our estimation, not equals to SI given what is transmitted, what is received, R, right? So this is the probability of error. Does that make sense? Right, so what is the probability that, so our estimation is not equals to what is sent, right? So basically, so this is an event, right? So this event basically equals to, okay, so what if we send a 0 and but our decision is a S1 hat, S1, right? And or our decision is the S0, actually we send a 1, right? So this basically means that. Okay, so this is the error. All right. Okay, so basically our decision rule we're going to use, because so basically what we got is a distribution of R, right? So basically we're going to use the distribution to design our optimal rule, right? So basically, we're going to use some Bayesian approach. So we call that the optimal Bayesian detection. So in particular, so what we're going to design is the so-called maximum a posteriori maximum a posteriori or map decision rule. Okay, who heard of that? Yeah, it's pretty famous, right? Probably understand that already. So who knows it? Okay, great. Yeah, basically, do you know how to derive it?
Kind of like induce a prior, and then you multiply it by like the generated like data likelihood, and then you choose the value that optimizes the posterior rather than just like the observed data. Like if you just do the observed data, it's like the MLE, right? It's like the maximum likelihood.
Yeah, so basically that is what we're going to do. Yeah, you're right. Yeah, we're going to derive it. So, okay. So here, this maximum a posteriori rule will basically minimize the probability of error. Okay, so you can see. So what we're going to do is that we're going to minimize this to get it. Okay, and I just want to say one more thing here. So what does this posteriori mean? So what is the opposite of it? Prior, right? Prior meaning that we know something beforehand, right? So this basically means that, the observation after the measurement, right? So this basically means that after the measurement, right? In other words, it basically means that, so we're going to determine what to do given R, right? R is what we know. Okay, so now let's see what we do. Okay, so basically what we're going to do is as follows. So basically we're going to minimize that, right? So what we do is that we're going to do the opposite. So minimizing the error is maximizing the probability that which one is sent. Okay, so basically this is what we're going to do. Right, so we're going to determine the index I, right? I is basically, yeah, Si and I would be the same, right? I mean, in terms of which one is sent, okay? So we're going to determine an optimal I based on this. Arg max over I. So then we're going to maximize a posteriori probability. Okay, so that is given by this. As I is sent, given R is received, right? So this one, so this probability is called a posteriori probability, or we call this APP. Okay, that makes sense. So basically, we're going to see, okay, now after receive R, so what is actually sent, and then we're going to maximize the probability of it. So that will minimize the error probability. Okay, so that's the idea. So, and oh, by the way, do you know this notation, argmax? So basically, it means that we need to maximize it over I, and then what I to maximize it is the output. Okay, so argmax. Okay, let's see how can we compute it. So first of all, can we compute it? Yet, right? So what we know is now this, right? Remember, so what we know is what is the distribution of R given which one is sent. We know this PDF first of all, PDF is not a probability, right? It's a probability density, right? And then, so here is kind of the opposite, right? So what we do want to know is given R, then what is sent, right? So can we know the distribution of that? Not directly, right? So it's the opposite, right? So if we know which one is sent, then we know what the distribution of R is, right? But now it's the opposite. Okay, given R, right? Remember, so R equals to Si plus N, right? So now, given, so this is received. So then what is the distribution of Si, right? This is the kind of thing we're asking, okay? So now let's see whether we can do it or not. So the reason we call it optimal Bayesian rule is Bayesian detection is that, so now we have to use the Bayesian rule to compute this guy, right? Because what we know is kind of something, exchanged there, right? So let's see what we can get from here by using the Bayesian's rule, right? Basically, Bayesian, in order to compute it, so the Bayesian rule tells us that, okay, so the probability of Si is sent and R is received divided by the probability that R is received, right? So this is equal to that, right? That correct? Any question from the first step? All right. Okay. And given this, so now let's let's try to compute it. Okay, so now we're gonna use the Bayesian rule again here. Okay, so we're gonna compute the probability of R given Si is sent times the probability of Si sent, right? And divide by PR. Right? So here we use the Bayesian rule again, right? This guy multiply given this guy and R, right? Okay, so now the challenge is to compute this guy, right? What is the probability of R here? Right? Remember, R is what we received, right? And what's the probability of R? Yeah, R is a Gaussian distribution, right? So R is a point on the Gaussian distribution, right? So let's say, yeah, R may not be a Gaussian. R is a Gaussian given Si, but it kind of, because of this n, right? So we know R is kind of this continuous distribution, right? So what's the probability here on each continuous distribution? Right? What is the probability of, because here we're asking the probability of this point, right? R is given, right? R is given. So what's the probability of this particular point for a continuous distribution? 0, right? Then we'll have like a 0 divided by 0, right? We cannot compute it. So basically what we do is that instead of computing exact probability of point, so we're computing a neighborhood of it. So the probability of this guy, right? So this is R. Okay, and then we denote the width of it is like delta, for example. And then when that delta goes to infinity, it goes to 0, then we can compute the ratio, right? So this is basically the idea, right? So what we can do here is that, so this equals to arg max I, and then, so the value here is the PDF, right? So basically, this is what we know, right? So remember, we know the PDF of, we know this guy, right? So this is a PDF. So basically what we have is that we use what we know there, R given Si is sent, right? And times the delta, and times this guy, P, Si is sent, right? And then divided by this guy, so it's FR times delta, right? FR is the PDF of R without condition. Okay, and from here we can see that delta got canceled, right? We don't need this delta anymore, right? So what we have here is FR given Si sent times the probability that Si is sent divided by probability of R. Oh, sorry, the PDF of FR, right? So now we need to be a bit more careful here, right? So things looks a little bit weird. Okay, so because things are combined together, right? So this guy is a probability, right? That we know, but this y is not a probability anymore. It's a PDF, right? So we cannot call that probability. So actually, we call that a likelihood. Likelihood. How to spell it? So this is the likelihood of R. Okay, given SI. Okay, send. All right. Okay, and now let's see what is our goal. Let's recall what is our goal. We need to pick an I to maximize the entire thing here, right? So now let's see, for this guy, does not depend on I, right? So it doesn't matter anymore. We can ignore that, right? Because it's not a function of I, right? So basically, what we can do is that we just ignore that and can get arg max only the numerator, right? We don't need a denominator anymore because it's not a function of I times psi send. Okay, and then we're done. So basically, now we need to find the I such that this guy is maximized. Okay, and we know this, right? So this is what we just computed before. And how about this one? The probability that SI is sent. Yeah.
We assumed it was 1/2 for each of them.
Yeah, we don't know that, right? So if we don't have any, so this is so-called prior information. So if we don't know that, we just assume that the probability of S0 send equals to probability S1 send, that equals to half. Okay, and then we just need to maximize that. Okay, so yeah, we're almost out of time. So now let's summarize a little bit, okay? So yeah, after all this derivation, so we kind of know how to find what is sent, right? We just want to find the value of R to maximize that, right? So we're going to see how to exactly maximize that in the next class, okay? But let's summarize what are the problems that are left, right? So we solved lots of problems already, right? What are the problems that are left, okay? We still have a few problems left. Okay, so the first problem is that, okay, so now we know the formula, okay, already. So the first problem is that, okay, how to use that formula to find the maximal, to find the optimal I, right? The first question I want to answer is that how to make decision using R, right? Or using that formula, okay? This is the first question that we're going to answer immediately in the next lecture. And the second question is that, so now we just assume f of t equals to S0 divided by the norm of F0, okay? It is optimal, right? Or how can we find how to find ft to get the best performance in general. Okay? So we're going to answer these two questions in our class, and that's it, almost. Okay? But there's another question, so that I mentioned before. The third question is that, is this architecture optimal? Yeah, what I mean is that the architecture of multiplying by a function and then do the integral. So is this architecture optimal? Right? So probably we're not going to answer this question in this class. So we're going to answer that in the class called digital communication. Right? So it's optimal in terms of some metric, like SNR and so on. Okay, so basically in the rest of this class, we're going to focus on these two problems and then see how to characterize the performance of it, right? To see what is the best performance. Okay, basically it's that, right? The best performance basically means that we're gonna find something to minimize the probability of error. Okay, and I think that'll be it for today. So see you next class.